If you're using this to fall asleep, that's literally why I make these. So subscribe maybe and tell me where you are and what time it is. I check comments and it's like Tokyo at dawn, Toronto at midnight, all at the same time. There's something perfect about pondering human evolution when your own brain is shutting down for the night. Think about that for a second. We live in the most technologically advanced period in human history. We've decoded our own genome, built computers that fit in our pockets, sent rovers to Mars that send back selfies. We have more knowledge at our fingertips than every ancient library combined. We've cured diseases, split atoms, figured out quantum mechanics. By every measurable standard, humans today are operating at peak cognitive performance, and yet our brains are physically smaller than those of our ancestors, who were painting on cave walls and hunting with stone-tipped spears. That's not supposed to happen. That's not how evolution is supposed to work. The standard story we tell ourselves about human evolution goes something like this. We climbed down from the trees, started walking upright, freed up our hands for tools, and our brains just kept getting bigger and bigger. From Australopithecus with their chimp-sized brains to Homo erectus to Neanderthals to us. A nice clean line going steadily upward. More brain equals more intelligence, equals more success, equals evolutionary victory. Simple, obvious, completely wrong. Because around 20,000 years ago, right after we'd reached our maximum cranial capacity, something changed. The trend reversed. Our brains stopped growing and started shrinking instead. Not slowly over millions of years, relatively quickly. In evolutionary terms, 20,000 years is basically yesterday. It's barely enough time for significant evolutionary change to occur through natural selection. And yet here we are, walking around with noticeably smaller brains than our recent ancestors. Scientists have known about this for decades, but for a long time they didn't talk about it much. It's one of those uncomfortable facts that doesn't fit the narrative. We like to think of human evolution as a success story, a tale of inevitable progress toward greater intelligence and capability. The idea that our brains might be shrinking feels wrong. It feels like we're going backward, like something went wrong with the program, like maybe evolution made a mistake, or maybe evolution didn't make a mistake, maybe something interrupted it. Maybe the process that was supposed to keep refining and enlarging the human brain got derailed somehow. Maybe we're living through an evolutionary transition that never quite completed. An upgrade that got stuck at 95% and just froze there while we went ahead and built civilization anyway. This is the mystery we're diving into tonight. Why did human brain growth stop 20,000 years ago? Why did it reverse? What does it mean that we're getting smarter while simultaneously getting smaller-brained? And the question that keeps anthropologists and evolutionary biologists up at night. Are we witnessing an evolutionary improvement or the beginning of a decline? The answers, and there are several competing theories, none of them proven, cut to the heart of what it means to be human. They touch on everything from diet to social organization, from climate change to the invention of agriculture, from the nature of intelligence itself to whether our species is still evolving, or if we've somehow managed to break free from evolutionary pressures entirely. Some researchers think the shrinkage is actually an upgrade, that we're building more efficient brains that can do more with less, like upgrading from a huge old desktop computer to a sleek laptop. Same processing power, smaller package. These scientists look at our shrinking brains and see optimization, refinement, evolutionary genius. Others point to dramatic changes in human lifestyle starting around the end of the last ice age, the shift from nomadic hunting and gathering to settled agriculture, The change in diet from varied wild foods to carbohydrate-heavy grain-based meals, the reduction in physical activity, the increase in population density. Maybe our brains responded to these new conditions by downsizing. Maybe we don't need the same cognitive hardware that our Ice Age ancestors required. Then there's the really interesting theory that we've essentially outsourced parts of our brain function to society itself. That when we developed complex language, writing, accumulated cultural knowledge, we created a kind of external hard drive for information storage. Maybe individual brains could afford to shrink because the collective intelligence of human civilization was taking on more of the cognitive load. And then there's the dark theory, the one that suggests maybe this isn't optimization at all. Maybe it's deterioration. Maybe we're actually getting dumber, but we've built enough technology and accumulated enough knowledge that we can coast on the achievements of our bigger-brained ancestors. Maybe we're like trust fund kids living off an inheritance we don't even understand. This theory makes people very uncomfortable, but we're going to look at it anyway because uncomfortable questions are often the most important ones. Over the next hour or so, we're going to explore all of these possibilities. We're going to dig into the fossil evidence, the genetic data, the archaeological record. We're going to look at what was happening to human society and human bodies right around the time our brains stopped growing. We're going to examine case studies from other species that experience similar changes, and we're going to confront the possibility that human evolution isn't the finished masterpiece we like to imagine, that maybe we're still a work in progress, or worse, a work interrupted. The human brain is the most complex object we know of in the universe. 3 pounds of wrinkled tissue containing roughly 86 billion neurons, each making thousands of connections to other neurons. It's what makes us us. It's where consciousness lives, where thoughts happen, where you exist. And for reasons we still don't fully understand, this magnificent organ reached its maximum size 20,000 years ago and has been shrinking ever since. So let's figure out why. Let's solve the mystery of the frozen brain. Let's talk about the most humbling fact in human evolution. Your brain is smaller than your ancestors' brains. Not by a little, by a lot. About 10 cents smaller, which doesn't sound like much until you realize we're talking about 150 cubic centimeters of missing brain tissue. That's roughly the size of a tennis ball. A tennis ball's worth of brain that your Ice Age ancestors had and you don't. 20,000 years ago, humans reached peak brain. Our ancestors, the Cro-Magnons, walked around with skulls housing brains that averaged 1,500 to 1,600 cubic centimeters. Some individuals pushed past 1,700 c. These weren't outliers or genetic freaks. This was normal. This was standard issue human hardware at the end of the last Ice Age. Compare that to modern humans. Today, the average human brain measures about 1,350 cubic centimeters. We've lost more than 10% of our cranial capacity in just 20,000 years. In evolutionary terms, that's not a gradual drift. That's a collapse, a freefall of grey matter happening so fast that it's actually one of the most rapid morphological changes in human evolutionary history. But here's what makes this really weird. Those 20,000 years ago, that's when humanity was supposedly at its most primitive, living in caves, wearing animal skins, hunting with stone-tipped spears. No agriculture, no writing, no cities, no civilization as we understand it. And yet, somehow, they needed bigger brains than we do to navigate their world. We've got smartphones and space stations and the internet, and we're doing it with significantly less neural hardware than our ancestors needed just to survive the Ice Age. So what were they doing with all that extra brain tissue? The archaeological evidence paints a picture that should make every modern human feel a little inadequate. The Cro-Magnons weren't primitive, not even close. These were people who created art so sophisticated that when modern humans first discovered it in the late 19th century, many scientists refused to believe prehistoric people could have made it. The cave paintings at Lascaux, Chauvet, Altamira. These aren't crude stick figures scratched onto rock walls. These are masterworks, animals rendered with perfect anatomical accuracy, capturing motion and behavior with an understanding that requires deep observation and artistic skill. The horses at Lascaux show muscle tension and movement. The lions at Chauvet display social dynamics, hunting behavior, emotional states. The bison at Altamira are painted with perspective and shading techniques that wouldn't be invented again until the Renaissance. And these paintings aren't just technically impressive. They're placed deep inside cave systems, in chambers that required navigating hundreds of meters through total darkness. The Cro-Magnons were creating art in locations that required sophisticated planning, light sources, scaffolding, and group coordination. This wasn't decoration. This was something else entirely. Something that required abstract thinking, symbolic reasoning, the ability to conceive of representing three-dimensional reality on a two-dimensional surface. The cognitive load for that kind of artistic creation is enormous. It requires mental rotation, spatial reasoning, planning, fine motor control, and the ability to hold complex visual information in working memory while translating it into physical marks. And they were doing this while maintaining the constant survival requirements of Ice Age existence. Hunting, gathering, tool-making, shelter construction, social coordination. The Cro-Magnons weren't just surviving, they were thriving intellectually in ways that required massive neural resources. Their tool technology tells the same story. The Upper Paleolithic toolkit that modern humans developed around 45,000 years ago and perfected by 20,000 years ago represents a level of technical sophistication that's easy to underestimate. We're not talking about picking up rocks and hitting things. These were carefully crafted implements that required understanding material properties, planning, and sequential processing. Take a simple stone blade. To create one, you need to select the right type of stone. Not just any rock will work. You need fine-grained material that fractures predictably. Flint, obsidian, chert. Then you need to prepare the core, removing flakes in a specific sequence to create the right angles and platforms. Then you strike it precisely, applying exactly the right amount of force at exactly the right angle to detach a blade with sharp parallel edges. One mistake and the entire core is ruined. You have to start over. The Cro-Magnons could produce dozens of identical blades from a single core. That's not just skill. That's procedural knowledge that has to be held in memory, refined through practice, and taught to the next generation. Each step in the process requires spatial reasoning, fine motor control, and the ability to predict how force will propagate through a crystalline structure. It's applied physics, materials science, and craftsmanship all wrapped together. And they weren't just making one type of tool. Archaeological sites from 20,000 years ago contain dozens of specialized implements, scrapers for processing hides, burins for engraving bone and antler, projectile points in multiple designs for different game, animals, bone needles with eyes for sewing fitted clothing, fish hooks, harpoons, spear throwers that use leverage principles to increase projectile velocity. Each tool represents a separate body of knowledge. Each requires different manufacturing techniques. The total cognitive load of maintaining this technological system across a population is staggering. You need people who specialize in tool making, teaching their skills to apprentices. You need knowledge-sharing networks to spread innovations. You need abstract language capable of conveying complex procedural information. But maybe the most impressive thing about Cro-Magnon cognition is something we can only infer from the evidence. They were managing incredibly complex social systems. Ice Age humans lived in groups of probably 30 to 50 individuals, but they maintained relationships with a much larger social network. Archaeological evidence shows raw materials being moved hundreds of kilometers from their sources. Shell beads from the Atlantic coast showing up at sites deep in continental Europe. Obsidian from volcanic regions appearing in areas hundreds of miles away. This wasn't random. This was systematic trade, which means the Cro-Magnons had to maintain relationships with people they might see only a few times in their lives. They had to remember who owed what to whom. They had to negotiate exchanges, probably using complex gift-giving systems that created obligations across generations. They had to track kinship relationships across multiple groups to know who was eligible for marriage alliances. Anthropologists call this the social brain hypothesis. The idea that much of human intelligence evolved specifically to handle the computational challenges of living in complex social groups. And the Cro-Magnons were managing social complexity that rivaled anything in the modern world just without writing or record keeping. Everything had to be held in memory. Every relationship, every obligation, every piece of knowledge about who's related to whom, and what the status relationships are between different groups. The cognitive load for that kind of social management is massive. Modern humans struggle with it even with written records and digital databases. The Cro-Magnons were doing it with nothing but their massively enlarged brains and oral tradition. And they weren't alone in having these enlarged brains. The Neanderthals, those robust, cold-adapted humans who had evolved in Europe, also had bigger brains than modern humans. Actually, on average, Neanderthal brains were even larger than Cro-Magnon brains. Some Neanderthal skulls show cranial capacities pushing past 1,700 cubic centimeters. These were people with genuinely massive brains, and they needed them. Neanderthal archaeological sites show the same kinds of cognitive sophistication as Cro-Magnon sites. Complex tools, evidence of symbolic thinking, burial practices that indicate belief in an afterlife or at least treatment of the dead as meaningful. They were using plant medicines as evidenced by chemical residues in their teeth. They were caring for injured and disabled group members, keeping alive individuals who couldn't contribute to food gathering, which suggests empathy and social responsibility. Most impressively, Neanderthals were master hunters of Ice Age megafauna, taking down woolly mammoths, woolly rhinoceros, giant cave bears. These weren't opportunistic kills. These were planned, coordinated hunts that required detailed knowledge of animal behavior, sophisticated communication, and the ability to work together under extremely dangerous conditions. One mistake, and someone dies. Everybody in the hunting party had to know their role, execute it perfectly, and trust that everyone else would do the same. That kind of coordination requires theory of mind, the ability to understand what other people are thinking and predict what they'll do. It requires planning across time, imagining future scenarios and preparing for them. It requires risk assessment, weighing the dangers of a mammoth hunt against the payoff of thousands of pounds of meat and fat that could keep a group alive through a brutal winter. All of this required massive neural resources, and both Cro-Magnons and Neanderthals had them. The question is, why? The answer probably lies in the environmental conditions of the Ice Age. From about 110,000 years ago until 12,000 years ago, the world was locked in glacial conditions. Northern Europe and North America were buried under ice sheets kilometers thick. Global temperatures were 5 to 10 degrees Celsius colder than today. Sea levels were 120 meters lower because so much water was locked up in glaciers. The geography of the world looked completely different, and it wasn't stable. Ice Age climate was characterized by rapid, dramatic swings. Within a single human lifetime, temperatures could crash or spike by several degrees. Rainfall patterns would shift. Animal migrations would change. What had been a productive hunting ground one year could become barren wasteland the next. The people who survived the Ice Age weren't just tough. They were cognitively flexible. They could adapt quickly to changing conditions. They could innovate new survival strategies when old ones stopped working. They could process enormous amounts of environmental information and make life or death decisions based on complex calculations about risk and reward. This kind of cognitive flexibility requires neural resources. Specifically, it requires a large prefrontal cortex capable of executive function, planning, and inhibitory control. It requires a large hippocampus for spatial memory and navigation across vast territories. It requires enlarged temporal lobes for language processing and social cognition. All of this means bigger brains, and bigger brains are expensive. Massively expensive. Brain tissue is metabolically costly to maintain. Your brain represents about 2% of your body weight but consumes about 20% of your total energy budget. That's an enormous investment. For evolution to favor bigger brains, the survival advantage they provide has to outweigh that massive energy cost. During the Ice Age, apparently it did. The timeline of human brain expansion supports this. 2 million years ago, our ancestors had brains around 600 cubic centimeters. Small, not much bigger than modern chimpanzees, but starting around 1.5 million years ago, brain size begins increasing. Homo erectus pushes past 900 cc. Homo heidelbergensis reaches 200 cc by 600,000 years ago. Then comes the split we talked about earlier. The bottleneck survivors diverging into 3 species: modern humans, Neanderthals, and Denisovans. And all 3 species show the same trend: steadily increasing brain size over hundreds of thousands of years. By 200,000 years ago, early modern humans have reached 400 cc. Neanderthals are pushing 500 c. By 20,000 years ago, at the peak of the last ice age, human brain size hits its maximum. Around 1,500 to 1,600 cc for Cro-Magnons, even larger for some Neanderthal populations. This wasn't random drift. This was directional selection. For 2 million years, evolution was consistently favoring bigger brains. Every generation, the individuals with slightly larger brains, slightly better cognitive abilities, slightly more capacity for learning and problem-solving, were having more surviving offspring. The selection pressure was relentless, and the Ice Age, with its constant environmental challenges and cognitive demands, was the final phase of that selection, the period when human brains reach their absolute maximum size. These were humans built for cognitive performance. Every aspect of their lives required intelligence, planning, knowledge, and social coordination. They had to track seasonal changes across vast territories, remember the locations of hundreds of water sources and food resources, maintain detailed knowledge of animal behavior and plant ecology, craft sophisticated tools from memory, teach complex skills to their children, manage social relationships across multiple groups, create and maintain cultural knowledge that could be passed down through generations. And they did it all with those massive, energy-hungry brains that represented evolution's greatest investment in neural tissue. For 20,000 years, this was the peak of human cognitive hardware, the golden age of the human brain, the moment when our species had evolved the largest, most powerful brains in the history of life on Earth. Then something changed, and everything we'd spent 2 million years building started to shrink. So modern humans won. We spread across every continent except Antarctica. We developed agriculture, built cities, created writing, domesticated animals, invented mathematics and astronomy. We became the undisputed masters of planet Earth. Our brains had carried us to the top of the food chain and beyond. And then something really weird happened. Our brains started shrinking. Not slowly, not gradually over millions of years like you'd expect from normal evolutionary processes. Fast. Shockingly fast by evolutionary standards. The archaeological evidence is undeniable. Around 20,000 years ago, human brain size began decreasing. By 10,000 years ago, the trend was unmistakable. And then around 3,000 years ago, the shrinkage accelerated dramatically. We're talking about losing roughly 150 cubic centimeters of brain volume. That's about 10% of our total brain size. Gone. To put that in perspective, that's equivalent to losing a chunk of brain tissue the size of a tennis ball from every human skull on the planet. The numbers are stark and disturbing. Your Cro-Magnon ancestors from 20,000 years ago, the ones who painted those magnificent cave paintings in Lascaux and Chauvet, they had average brain volumes of about 1,500 cubic centimeters. Modern humans today average around 1,350 cubic centimeters. We're literally smaller brained than our recent ancestors. And here's where it gets even stranger. The shrinkage wasn't uniform across all human populations. Different groups experienced different rates of brain size reduction, and they experienced them at different times. This tells us something important. Whatever caused our brains to shrink, it wasn't a single global event. It was something that happened repeatedly, independently, in different places, following similar patterns but on different timescales. In Europe, the most dramatic shrinkage occurred between 10,000 and 3,000 years ago, precisely coinciding with the spread of agriculture from the Middle East into Central and Northern Europe. Skeletal remains from hunter-gatherer populations in Scandinavia show significantly larger cranial capacities than remains from early farming communities in the same regions just a few thousand years later. In East Asia, the pattern was similar but slightly offset in time. Chinese skeletal collections show the most dramatic brain size reduction, occurring between 8,000 and 2,000 years ago, tracking with the independent development of rice agriculture in the Yellow River Valley. In the Americas, where agriculture developed even later and in some regions never developed at all, the brain size reduction was less dramatic. Hunter-gatherer populations in North America maintained larger average brain sizes than their agricultural counterparts in Mesoamerica and South America. This geographic correlation with agricultural development isn't coincidental. It's telling us something crucial about what happened to human evolution when we stopped wandering and started farming. But before we get to causes, let's look at exactly what changed physically. Because it wasn't just that skulls got smaller overall, the shape changed too, and that shape change reveals something fascinating about what was happening inside those shrinking skulls. Anthropologists examining thousands of skulls from different time periods have mapped these changes in detail. The most obvious change is in the frontal bone, the part of the skull that houses your frontal lobes, the region responsible for planning, decision-making, and complex reasoning. In hunter-gatherer skulls from 20,000 years ago, the frontal bone projects forward prominently, creating a high, rounded forehead. In agricultural populations from 5,000 years ago, the frontal bone is flatter, more vertical. The skull appears more graceful, less robust overall. The temporal region, housing the temporal lobes responsible for memory and language processing, also shows reduction, though less dramatic than the frontal area. The occipital region at the back of the skull, which houses the visual cortex, shows the least change. This tells us the shrinkage wasn't evenly distributed. Different brain regions were affected differently. Most intriguingly, the interior structure of the skull changed too. CT scans of ancient skulls reveal that brain case shape became more spherical over time, less elongated. The brain didn't just get smaller, it got reorganized, reshaped, restructured. Neural tissue was redistributing itself inside the cranium, possibly becoming more densely packed in certain regions while thinning in others. But here's what really made scientists sit up and take notice. This pattern, this combination of overall size reduction with specific shape changes, looked familiar. They'd seen it before, not in human evolution, but in animal domestication. Take wolves and dogs. Wolves have larger brains than dogs, about 30% larger on average relative to body size. When humans domesticated wolves over thousands of years, selecting for tameness and trainability, their brains shrank. Not because they became stupider, but because domestication changed what kinds of brain structures were necessary for survival. Or consider wild boars and domestic pigs. Same pattern. The wild ancestors have significantly larger brains than their domesticated descendants. Same with wild chickens and domestic chickens, wild cattle and domestic cattle, wild horses and domestic horses. Every single animal that humans have domesticated shows the same trend. Reduced brain size, especially in regions associated with fear response, aggression, and independent problem solving. The domesticated versions aren't less intelligent in any simple sense. Dogs can do things wolves can't, like understand human pointing gestures and read human facial expressions. But they've lost certain capabilities that wild animals need. Heightened alertness, constant wariness, the ability to independently assess and respond to novel threats. So here's the uncomfortable question that emerged from this research. What if humans domesticated themselves? The self-domestication hypothesis suggests that as humans developed agriculture and permanent settlements, they inadvertently began selecting for temperamental traits similar to those we selected for in animals, specifically reduced aggression, increased cooperativeness, and greater tolerance for living in close proximity to large numbers of other humans. Think about what happens when you try to put too many wild animals in too small a space. They fight. They establish rigid dominance hierarchies. Many die from stress-related illness. Most refuse to breed in captivity. Wild animals are not psychologically equipped to handle high-density living. But humans 10,000 years ago started doing exactly that. They were abandoning the low-density, small-group lifestyle that had characterized the previous 2 million years of human evolution. They were crowding together in villages, then towns, then cities. Populations that had numbered in the dozens were suddenly living in communities of hundreds, then thousands, then tens of thousands. Under these conditions, the most aggressive, least cooperative individuals would have been at a severe disadvantage. You can't constantly fight everyone around you when you're living in a village of 200 people. You'd be ostracized, expelled, maybe killed. The archaeological record from early agricultural communities shows evidence of exactly this kind of social control. burial sites contain individuals with execution-style injuries, suggesting communities were actively eliminating highly aggressive members. Meanwhile, individuals who could tolerate crowding, cooperate with non-relatives, and suppress aggressive impulses would thrive. They'd be more likely to maintain social relationships, participate in collective activities, and ultimately reproduce successfully. Over hundreds of generations, this would constitute powerful selection pressure for temperamental domestication. And here's where it connects to brain size. The neural systems that support constant alertness, hair-trigger threat response, and aggressive competition are expensive. They require lots of neural tissue, particularly in the prefrontal cortex and amygdala. If you're living in a safe, predictable agricultural community, rather than wandering dangerous wilderness, you don't need those systems running at full capacity anymore. Natural selection would favor more efficient brains that devoted less tissue to threat detection and more to social cognition and cooperation. This would explain not just the size reduction, but the specific pattern of reduction. The frontal lobes, heavily involved in aggression control and threat assessment, show the most dramatic shrinkage. The temporal lobes, crucial for social communication as memory, show less. The visual cortex, still necessary for everyday perception, shows minimal change. It would also explain why the shrinkage tracked so closely with agricultural development. The denser the populations became, the stronger the selection pressure for domesticated temperament. Early agricultural communities had populations 10 to 50 times larger than hunter-gatherer bands. By the time we get to early cities like Uruk or Mohenjo-Daro, with populations in the tens of thousands, the selection pressure would have been enormous. The physical evidence supports this timeline. Skulls from pre-agricultural populations show not just larger brains, but more robust facial features, heavier brow ridges, more prominent jaw muscles. These features are associated with higher testosterone levels and more aggressive temperament. As agriculture spreads, these features diminish. Faces become flatter, more gracile. Brow ridges reduce. Jaw muscles weaken. The entire skull becomes what anthropologists call feminized, taking on characteristics more typical of females than males. This feminization is exactly what we see in domesticated animals. It's one of the key markers of the domestication syndrome, a suite of traits that appear repeatedly when wild animals are bred for tameness. Floppy ears, piebald coloring, reduced sexual dimorphism, and yes, smaller brains, especially relative to body size. But not everyone agrees that smaller means domesticated or that domestication necessarily means decline. A vigorous debate has been raging in anthropology for decades about what this brain shrinkage actually means for human cognitive capabilities. Some researchers argue we're looking at genuine cognitive decline. They point out that the most dramatic brain size reduction occurred during periods of significant cultural regression. The European Bronze Age collapse around 1200 BCE coincided with accelerated brain shrinkage. The late Roman period saw continued reduction, even as literacy declined and technological knowledge was lost. Maybe smaller brains really did mean reduced capability, at least in some contexts. Others vehemently disagree. They argue we're confusing quantity with quality. Brain size doesn't directly correlate with intelligence across species, or even within species. Neanderthals had larger brains than modern humans, but we outcompeted them. Einstein's brain was actually smaller than average. What matters isn't how much brain tissue you have, but how efficiently it's organized. According to this view, what we're witnessing isn't decline, but optimization. The human brain is being streamlined, refined, made more efficient. Redundant neural connections are being pruned. Brain regions are being reorganized for more efficient processing. We're not losing capability, we're losing excess capacity we no longer need. Think of it like computer processors. The first computers filled entire rooms and had less computing power than your phone. Modern processors are millions of times smaller, but infinitely more capable. Miniaturization doesn't mean reduced performance, it means improved efficiency. The same could be true for brains. Those massive Cro-Magnon brains might have been powerful but inefficient, burning enormous amounts of energy to accomplish tasks that more compact modern brains can handle, with less tissue and lower metabolic cost. Remember, your brain uses about 20% of your body's total energy, despite being only 2% of your body weight. Any reduction in brain size that doesn't reduce function represents significant energy savings, and there's evidence supporting the efficiency argument. While overall brain size decreased, some specific regions actually increased in relative size. Brain imaging studies comparing modern skulls with ancient ones show that regions associated with language processing, specifically Broca's area and Wernicke's area, have maintained or even slightly increased their relative volume, even as total brain size decreased. Similarly, regions associated with fine motor control and tool use show less shrinkage than other areas. This suggests a reorganization rather than simple reduction. The brain was redistributing its resources, maintaining capacity in areas that remained crucial while reducing tissue in areas that had become less critical. The debate comes down to this fundamental question. Did we lose something important when our brains shrank, or did we simply shed unnecessary weight? The pessimists point to the correlation with agricultural decline in cognitive diversity. Hunter-gatherers need to maintain extensive environmental knowledge, complex mental maps of vast territories, detailed understanding of hundreds of plant and animal species. Early farmers could survive knowing far less. They cultivated a few crop species, tended a few domestic animals, lived in one location their entire lives. The cognitive demands were different, arguably reduced in certain domains. The optimists counter that agriculture introduced new cognitive demands that more than compensated for any losses. Managing crop cycles requires abstract thinking about time and planning ahead across seasons. Living in large communities demands sophisticated social intelligence and theory of mind. Developing trade networks requires numerical reasoning and record keeping, which eventually led to writing and mathematics. Agriculture didn't make us dumber, it made us different kinds of smart. Both sides can point to evidence supporting their position, and honestly, they're probably both partly right. Human cognition almost certainly changed as our brains shrank. We probably did lose some capabilities while gaining others. The question is whether the net result represents progress, decline, or just change. What's undeniable is that something fundamental shifted in human evolution around 20,000 years ago, and that shift accelerated dramatically with agriculture. Our brains, which have been steadily growing for 2 million years, suddenly reversed course. The organ that had made us the dominant species on the planet began shrinking, and it's still shrinking today, though the rate may have slowed in recent centuries. We went from being the big-brained hunters and explorers who painted masterpieces on cave walls and tracked animals across continents to being smaller-brained farmers and city dwellers who invented writing, mathematics, and civilization. Whether that represents an evolutionary triumph or a Faustian bargain, we're still trying to figure out. But the shrinkage itself is just the beginning of the mystery. Because the real question isn't just why our brains got smaller, it's whether they're still changing, still evolving, and if so, In what direction? Because evolution didn't stop 20,000 years ago. It didn't even stop 3,000 years ago. It's still happening right now, in every human population on Earth. And the changes might be accelerating. So here's the first theory about why our brains stopped growing, and honestly, it's the most optimistic one. Maybe, just maybe, our brains didn't stop evolving. Maybe they just got smarter about how they evolved. Think about computers for a second. The first digital computer, the ENIAC, weighed 30 tons and filled an entire room. It could perform about 5,000 calculations per second, which seemed miraculous at the time. Your smartphone, which weighs maybe 200 grams and fits in your pocket, can perform billions of calculations per second. It's not bigger. It's better, more efficient, more densely packed with processing power per cubic centimeter. What if that's exactly what happened to the human brain 20,000 years ago? This is called the neural efficiency hypothesis, and it's gained serious traction among neuroscientists over the past decade. The basic idea is simple but profound. Size isn't everything. What matters is how your neural tissue is organized, how densely connected it is, how efficiently it processes information. A smaller brain that's wired more intelligently could theoretically outperform a larger brain that's using outdated architecture. Because here's the thing about brain size that nobody really talks about. More neurons don't automatically mean more intelligence. If that were true, whales would be writing symphonies and elephants would be building spaceships. Sperm whales have brains that weigh 17 pounds, 5 times heavier than human brains. But nobody's arguing they're 5 times smarter than us. What matters isn't the number of neurons, it's how those neurons are connected. It's the density and quality of the connections, the synapses, the neural pathways that shuttle information around your skull at lightning speed. It's the architecture, not the square footage. Modern brain imaging technology has given us unprecedented insight into this architecture. When researchers use diffusion tensor imaging to map the connections in human brains, they're seeing something remarkable. Modern human brains show incredibly dense connectivity patterns, particularly in regions associated with higher cognitive functions. Language processing areas, abstract reasoning centers, regions involved in planning and future simulation. These areas aren't necessarily larger than they were 20,000 years ago. They're more intricately connected, more efficiently wired. Think of it like upgrading from a city where every road is a 2-lane street to a city with a sophisticated network of highways, interchanges, and express lanes. You can move more traffic through less space if your routing system is intelligent. The key process here is called synaptic pruning, and it's something your brain has been doing since you were born. When you're a baby, your brain goes absolutely crazy generating connections between neurons. It creates far more synapses than you'll ever need, connections between every possible pair of neurons that might someday need to communicate. This creates a brain that's incredibly plastic, capable of learning anything, but also incredibly inefficient. Then comes the pruning. Throughout childhood and adolescence, your brain systematically eliminates connections you're not using. It's not destroying neurons, it's just cutting the unnecessary wiring between them. The synapses you use frequently, the ones that carry important information, get strengthened and maintained. The ones you rarely use get eliminated. By the time you're an adult, you've lost somewhere between 40 and 50% of the synapses you had as a young child. But you're not less intelligent. You're more intelligent, more focused, more efficient. Your brain has figured out which connections matter and optimized around them. Now imagine this process happening not just during individual development, but across evolutionary time. natural selection favoring brains that could do more with less, brains that were better at pruning unnecessary connections and strengthening critical pathways, brains that achieved the same cognitive performance with reduced volume. This would have been an enormous evolutionary advantage. Because here's something that's easy to forget. Your brain is expensive, metabolically expensive. That 3-pound organ sitting in your skull represents about 2% of your body weight, but it consumes roughly 20% of your total energy budget. It's burning through glucose and oxygen at a staggering rate, even when you're just sitting still. Throughout human evolution, calories were the ultimate limiting resource. Food was never guaranteed. Our ancestors spent enormous amounts of time and energy just trying to find enough to eat. Any adaptation that reduced caloric requirements without sacrificing survival capacity would spread like wildfire through the population. A brain that maintained the same intelligence while using 10% less energy. That's a massive advantage. Over thousands of generations that reduced energy demand could make the difference between surviving a harsh winter or starving to death. Between being able to travel long distances to find new resources or being stuck in one depleting territory. The efficiency hypothesis suggests that around 20,000 years ago, human brains hit a kind of optimization threshold. We'd accumulated enough beneficial mutations for neural efficiency, enough improvements in synaptic architecture, that our brains could start shrinking without losing any cognitive capacity. Maybe even while gaining some. We see hints of this in the changing ratio between grey matter and white matter in the human brain. Grey matter is the stuff that does the processing, the actual neuron cell bodies where computation happens. White matter is the wiring, the myelinated axons that connect different brain regions and allow them to communicate. Studies comparing ancient skulls to modern ones suggest that while overall brain volume decreased, the relative proportion of white matter might have increased. This would be consistent with brains becoming more interconnected, more efficiently networked, even as they got smaller. It's not about having more processors, it's about connecting the processors you have more intelligently. And we have evidence from living species that this kind of efficiency can produce remarkable results. Look at crows. Their brains weigh about 7 grams, roughly 0.5% of what a human brain weighs. But crows can use tools, solve multi-step puzzles, remember human faces for years, even hold grudges against people who've wronged them. They can plan for future events, and modify their behavior based on what they think other crows know. They're not doing this with massive brains. They're doing it with incredibly dense neural packing. Bird brains, it turns out, are organized completely differently from mammal brains. Instead of our layered cortex structure, they have densely packed clusters of neurons that achieve similar or better connectivity with far less volume. It's a different architectural approach to the same problem. Or consider octopuses. Completely alien nervous systems distributed across their arms with no centralized brain structure like ours. Yet they show problem-solving abilities that rival many vertebrates. They can navigate mazes, open containers, even recognize individual humans. All with a neural architecture that's fundamentally different from anything in our evolutionary lineage. These examples prove something important. Intelligence isn't locked to a specific brain size or structure. It emerges from efficient information processing, regardless of how that processing is physically implemented. If evolution could produce crow-level intelligence in a 7-gram brain, there's no reason it couldn't maintain or even improve human intelligence in a slightly smaller brain. The neural efficiency hypothesis also helps explain something puzzling about human evolution. We didn't just shrink uniformly. Different parts of the brain shrank at different rates. Some regions, particularly the frontal cortex and areas involved in language, seem to have maintained their volume better than others. Meanwhile, sensory processing areas and some motor control regions shrank more dramatically. This pattern makes sense if evolution was optimizing for efficiency. Areas critical for uniquely human cognition, language, abstract reasoning, social intelligence, those got maintained or even refined. Areas that were less critical or that could achieve the same results with fewer neurons, those got streamlined. It's not random shrinkage. It's targeted optimization. Modern genetics research is starting to identify specific genes that might be involved in this process. Genes that regulate synapse formation and pruning. Genes that control the myelination of axons, affecting how quickly signals travel between brain regions. Genes that influence the density of dendritic connections, the branching structures that let neurons receive information from multiple sources. Some of these genes show evidence of recent selection in human populations, specific variants that appeared relatively recently, within the last 20,000 to 30,000 years, and then spread rapidly through populations. This is exactly what you'd expect to see if evolution was actively refining human neural efficiency during the period when brains were shrinking. But here's where the theory gets really interesting. If our brains have been getting more efficient rather than less intelligent, we should be able to measure that somehow. And maybe we can. Cognitive archaeologists study ancient human behavior by looking at the artifacts and evidence left behind. Tool complexity, artistic sophistication, signs of abstract thinking and symbolic behavior. And what they find is that human cognitive abilities didn't decline when brains started shrinking. If anything, they accelerated. The period from 20,000 years ago to present shows an explosion of human innovation. More sophisticated tools, more complex art, the development of agriculture, writing systems, mathematics, architecture. Everything that we associate with advanced human civilization emerged during the period when our brains were supposedly getting smaller. That's not what you'd expect if the shrinkage represented cognitive decline. It's exactly what you'd predict if the shrinkage represented a shift toward greater efficiency. Brains that could do more with less, supporting more complex thought while consuming fewer resources. Consider language. Linguistic analysis suggests that the complexity and sophistication of human languages has, if anything, increased over the past 20,000 years. Modern languages show intricate grammatical structures, huge vocabularies, the ability to express abstract concepts with remarkable precision. We don't have recordings of prehistoric speech, obviously, but the linguistic diversity and complexity we see in modern hunter-gatherer societies suggests their cognitive abilities are identical to ours, despite living lifestyles similar to our distant ancestors. Or look at innovation rates. The pace at which humans develop new technologies has accelerated dramatically over time. This could be because we have larger populations now, more people to generate ideas. But it could also reflect enhanced cognitive capacity, brains that are better at seeing connections, identifying patterns, applying knowledge from one domain to solve problems in another. The efficiency hypothesis suggests that what looks like stagnation, brains stopping their growth, might actually be refinement, evolution hitting on a better design principle and then optimizing the hell out of it for 20,000 years. Not building bigger engines, but building engines that get more horsepower per litre of displacement. There's also a developmental angle here that's worth considering. Modern human children have longer childhoods than our ancestors did. We take longer to reach physical maturity. We stay dependent on our parents for more years. This extended childhood is metabolically expensive. Parents have to support non-productive offspring for longer periods, but that extended childhood might be exactly what allows our more efficient brains to develop properly. The complex synaptic pruning and optimization that creates a highly efficient adult brain might require more time, more experience, more opportunities for learning during development. A smaller but more sophisticated brain might need a longer construction period. So evolution might have made a trade-off. Reduce adult brain size, which saves energy throughout adult life, but extend childhood development, which costs energy in the short term but pays off with better optimized neural architecture. Over a lifetime, the energy savings from a more efficient adult brain could more than compensate for the extended childhood. None of this is proven definitively. We can't directly measure the neural efficiency of people who died 20,000 years ago. We can't run cognitive tests on them or map their synaptic density with modern imaging technology. We're inferring, making educated guesses based on skull measurements, archaeological evidence, and what we know about how brains work. But the efficiency hypothesis has something going for it that makes it appealing. It fits the data better than assuming our ancestors were simply smarter because they had bigger brains. It explains why human cognitive abilities continued advancing even as brain size declined, and it aligns with what we know about evolutionary principles. Evolution doesn't optimize for size, it optimizes for fitness, for survival and reproduction. And a more efficient brain, one that could maintain intelligence while reducing energy costs, would be more fit in almost any environment our ancestors faced. The computer analogy keeps coming back because it's so apt. Nobody thinks the massive room-size computers of the 1950s were more powerful than modern laptops just because they were bigger. We understand that technological progress often means miniaturization, efficiency, doing more with less. Why should biological evolution be any different? Maybe our brains didn't stop growing. Maybe they just finished growing and started getting better. But what if the answer isn't about neural efficiency at all? What if something far more fundamental changed about being human? Something we do every single day, multiple times a day, without even thinking about it. Eating. Because here's the thing about our ancestors with those massive 1,500 cubic centimeter brains. They didn't get those brains by accident. Brains are incredibly expensive organs. Your brain represents about 2% of your body weight, but consumes roughly 20% of your total energy. That's insane. No other organ comes close to that energy demand. A big brain requires serious fuel, and for hundreds of thousands of years, our ancestors were providing exactly that. The diet of a Paleolithic human was radically different from anything we eat today. Picture this. You're living 30,000 years ago, peak brain size era. Your diet consists almost entirely of wild game, fish, nuts, seeds, fruits, and whatever edible plants you can forage. The meat you're eating isn't like modern beef or chicken. These are wild animals, lean and muscular, with completely different fat profiles. Wild game has higher concentrations of omega-3 fatty acids, lower overall fat content, and vastly more diverse protein structures than domesticated animals. When you take down a mammoth or wild horse, you're not just eating muscle meat, you're eating organ meats, brain tissue, bone marrow, all the parts that modern people have forgotten are edible. And those parts are packed with nutrients that directly support brain development. Brain tissue especially is incredibly rich in DHA, an omega-3 fatty acid that's absolutely critical for neural growth and maintenance. Our ancestors were literally eating the raw materials their brains needed to stay large and complex. The variety was staggering. A typical hunter-gatherer might consume hundreds of different plant and animal species over the course of a year, each one providing a unique nutritional profile, different combinations of vitamins, minerals, proteins, and fats. This dietary diversity meant their bodies, and especially their brains, had access to virtually every nutrient needed for optimal development. Nothing was missing from the equation. Then, around 12,000 years ago, everything changed. The agricultural revolution. We call it a revolution, and it was, but not necessarily in a good way. For brain development, it might have been a disaster. Agriculture meant settling down. It meant planting fields of grain, domesticating animals, building permanent settlements. For the first time in human history, we could support large populations in relatively small areas. Population exploded. Civilization became possible. All those things we think of as human progress, cities, writing, technology, they all flow from agriculture. But here's what also happened. Dietary diversity collapsed. Instead of eating hundreds of different species, agricultural populations ate primarily one or two staple crops. Wheat in the Middle East and Europe, rice in Asia, corn in the Americas. Maybe some domesticated animals if you were lucky, supplemented by whatever you could grow in a garden or forage from increasingly depleted wild spaces. The nutritional consequences were immediate and severe. Agricultural populations show clear signs of nutritional stress in their skeletal remains. They were shorter than their hunter-gatherer ancestors. Their bones were less dense. Their teeth were worse, riddled with cavities from all those starchy grains. And their skulls began to change in ways that tell a troubling story. The average agricultural skull is smaller than the average hunter-gatherer skull from the same region. Not just brain case size, but overall cranial architecture. Jaws became smaller and less robust. Faces became flatter and less projecting. The entire structure of the human head began to shift in response to the new diet. And it wasn't just about total calories. Agricultural populations could produce more food overall than hunter-gatherers, that's why they could support larger populations. But that food was nutritionally inferior. Grains are primarily carbohydrates. They provide energy, but they're relatively poor in the specific nutrients that brains need. Protein content is lower. Fat profiles are completely different. Most critically, many of the vitamins and minerals essential for neural development are either absent or present in much lower concentrations than in wild foods. Take protein diversity. Hunter-gatherers eating wild game were consuming incredibly complex protein structures, hundreds of different amino acid combinations from dozens of different animal species. Their bodies had a rich palette of building blocks to work with when constructing neural tissue. Agricultural populations eating primarily grain, and maybe one or two domesticated animal species? That protein diversity collapsed to a fraction of what it had been. The shift in fat consumption was even more dramatic. Wild game, nuts, and fish provided abundant omega-3 fatty acids, the building blocks of brain tissue. Grain-based diets, especially once supplemented with domesticated animal fats, shifted the balance heavily toward omega-6 fatty acids. Modern nutritional science has shown that the ratio between omega-3 and omega-6 fats matters enormously for brain health. Too much omega-6 relative to omega-3, and you get inflammation, reduced neural plasticity, impaired brain development. Our agricultural ancestors didn't know about omega-3 ratios. They just knew that grain kept them from starving and could be stored through winter. But their brains knew something was wrong. The raw materials weren't there anymore. But the diet story goes even deeper. It's not just what we were eating, it's how we were eating it. Food processing changed everything about the mechanical demands of eating, and those mechanical demands shaped our skulls in ways that directly affected brain size. Hunter-gatherers ate tough, fibrous foods, raw or lightly cooked plant materials, meat that required serious chewing effort. This constant mechanical stress on the jaw did something important. It stimulated bone growth throughout the facial skeleton and cranium. Big, robust jaws require big, robust skulls to anchor them, and bigger skulls meant more room for brains. Agricultural foods, especially once people figured out how to process them, were much softer. Grinding grain into flour, cooking it into porridge or bread, these techniques created foods that required far less chewing effort. Over generations, this reduced mechanical stress led to smaller, more gracile facial structures. Jaws shrank. The muscle attachments that anchored jaw muscles to the skull reduced. The entire front of the skull became smaller and less robust. And here's where it gets interesting. Skull shape matters for brain size. The human skull isn't just a rigid box. It's a dynamic structure that responds to mechanical forces during development. The forces generated by powerful jaw muscles actually help shape the growing skull, pulling it wider, stimulating bone growth in the cranial vault. Reduce those forces, and you reduce the stimulation for skull growth. Modern humans have significantly weaker bite forces than our Paleolithic ancestors. Our jaw muscles are smaller. The bone ridges they attach to are less pronounced, and our cranial vaults, the part of the skull that houses the brain, are correspondingly smaller. Some researchers think this isn't just correlation. They think the shift to softer, processed foods directly caused skull reduction, which in turn constrained brain size. Your brain doesn't shrink because it needs to be smaller. It shrinks because the skull it's growing in is smaller, and the skull is smaller because the mechanical forces that shaped it during evolution have been removed. This is called the masticatory functional hypothesis, and it's got some serious evidence behind it. Studies of modern populations show direct correlations between dietary toughness and cranial size. Populations that still eat relatively tough, unprocessed foods have larger jaws and skulls than populations eating soft, highly processed diets. This difference appears within just a few generations, suggesting the effect is developmental, not evolutionary. Your skull grows in response to the forces placed on it during childhood and adolescence. Feed a population soft foods that require minimal chewing, and you get smaller jaws and smaller skulls, generation after generation of this, and you're looking at significant population-level changes in cranial architecture. But we're not done with diet yet, because there's another player in this story that might be even more important than protein or jaw mechanics. Carbohydrates. Agricultural diets aren't just lower in protein and fats, they're vastly higher in carbohydrates. Grains are basically pure carbohydrate once you process them, and carbohydrates do something specific to human metabolism. They spike blood sugar and insulin in ways that wild foods never did. High carbohydrate intake, especially the refined carbohydrates that became common once industrial food processing emerged, fundamentally alters brain chemistry. Glucose metabolism changes. Insulin signaling in the brain shifts. Over time, these metabolic changes can affect neural structure and function in ways we're only beginning to understand. Some researchers think chronic high carbohydrate consumption might actually inhibit certain types of brain development. The brain evolved to run on a mixed fuel system, glucose from carbohydrates, yes, but also ketones from fat metabolism. During the Paleolithic period, humans probably cycled between these fuel sources regularly. Feast on a kill and you're running on glucose. Fast for a few days while hunting and you shift to ketone metabolism. That metabolic flexibility might have been important for maintaining brain size. Ketone metabolism produces different signaling molecules than glucose metabolism. Some of these molecules, like brain-derived neurotrophic factor, directly stimulate neural growth and maintenance. Constant high glucose availability from agricultural diets might have reduced the metabolic flexibility that supported large brains. Then there's the lifestyle piece. Agriculture didn't just change what we ate, it changed how we lived, and those changes brought new evolutionary pressures that might have favoured smaller brains. Settlement meant population density. For the first time, humans were living in large groups, hundreds or thousands of people in relatively small areas. That population density created perfect conditions for infectious disease. Measles, smallpox, tuberculosis, all the epidemic diseases that would eventually kill millions, they emerged from agricultural settlements where humans lived in close contact with each other and with domesticated animals. Disease became a major evolutionary pressure. Surviving epidemics required robust immune systems, and immune systems are expensive to maintain. They consume resources, energy, and metabolic capacity. In an environment where food quality had already declined, bodies faced a choice: invest limited resources in maintaining a massive energy-hungry brain, or invest them in immune function that might save your life during the next epidemic. Evolution chose survival. Immune systems got more sophisticated. Brains got smaller. It's a brutal trade-off, but it makes perfect sense from a natural selection perspective. A slightly smaller brain is better than a corpse. The reduction in physical activity probably played a role too. Hunter-gatherers walked, ran, climbed, and engaged in constant physical activity. That activity wasn't just exercise. It was fundamentally connected to cognitive function. Physical activity stimulates production of growth factors that support neural health. It improves blood flow to the brain. It triggers the release of neurotransmitters that enhance learning and memory. Agricultural populations were more sedentary. Not completely inactive, farming requires work, but the constant varied physical challenges of a hunting and gathering lifestyle were replaced with repetitive agricultural labour. Less stimulation for the brain, less support for maintaining large complex neural structures. Modern life has taken this sedentary trend to extremes. Today, many people barely move at all compared to our ancestors. We sit at desks, we ride in cars, we've engineered physical activity almost completely out of daily life, and brain size has continued to shrink. But perhaps most troubling is what's happening right now. Modern industrial diets might be taking the agricultural revolution's nutritional problems and amplifying them to unprecedented levels. We're not just eating processed grains anymore. We're eating ultra-processed foods, created in factories from ingredients that barely resemble anything found in nature. High-fructose corn syrup, hydrogenated vegetable oils, artificial flavors and preservatives. These aren't just nutritionally inferior. Many of them might be actively harmful to neural development. Studies of modern populations show declining nutrient density in foods. The vegetables we eat today contain lower concentrations of vitamins and minerals than the same vegetables did 50 years ago. Industrial agriculture has selected for yield and appearance, not nutritional content. The animals we eat are fed grain instead of grass, fundamentally altering their fat profiles and reducing omega-3 content. Some researchers worry we're creating a cascading nutritional crisis that's affecting brain development across entire generations. Children today are eating diets that are even more removed from Paleolithic nutrition than agricultural diets were. More processed, more refined, more depleted of the specific nutrients brains need to develop properly. Is this causing measurable harm? The evidence is mixed and controversial. Some studies show declining cognitive abilities in specific domains. Others show improvements, probably due to better education and reduced childhood disease. But the question hangs in the air, unanswered and unsettling. Are we starving our brains of what they need to reach their full potential? There's a darker possibility too. What if brain shrinkage isn't just about diet-changing brain size? What if it's a feedback loop? Smaller brains make worse decisions about food. Worse food choices lead to smaller brains in the next generation. Round and round, each generation slightly worse off than the last. This is speculative, but it's not crazy. We know that nutritional deficiencies during pregnancy and early childhood can permanently affect brain development. We know that modern diets are depleted in many nutrients compared to wild foods. We know that brain size has continued to shrink even in recent centuries. Put it all together, and you get an uncomfortable picture. Maybe we're not just documenting brain shrinkage that happened in the past. Maybe we're participating in it, right now, every time we choose processed convenience over nutritional density. The agricultural revolution gave us civilization. It let us build cities, develop writing, create all the technology and culture we associate with being human. But it came with a cost, written in the shrinking dimensions of our skulls, recorded in the fossil record as clearly as words on a page. We traded brain size for population size. We traded cognitive potential for agricultural productivity. And we might still be paying that price, generation after generation, as our heads continue their slow, inexorable shrinkage. But diet isn't the only answer, because there's another revolution that happened alongside agriculture, one that might have changed our brains even more profoundly, the social revolution, the moment when we stopped needing to remember everything ourselves because we could rely on the collective knowledge of our communities, and that's where things get really interesting. But what if we're thinking about this all wrong? What if individual brain size isn't really the measure that matters anymore? Because here's the thing. Around 20,000 years ago, something unprecedented was happening to human societies. We weren't just getting better at surviving. We were becoming fundamentally different kinds of organisms. For millions of years, human evolution had followed a clear pattern. The smartest individuals survived. The ones with better memory, faster problem-solving abilities, more sophisticated spatial reasoning. They were the ones who found food when others starved, who remembered which plants were poisonous, who could track prey across vast distances by reading subtle signs in the landscape. Every calorie of energy you invested in brain tissue had to pay for itself in survival advantages. Your brain was your personal survival computer, and natural selection was constantly upgrading the hardware. But then we invented something that changed everything. We learned to share our brains with each other. The revolution didn't happen all at once. It started with language, probably sometime during that post-bottleneck recovery period we talked about earlier. But by 20,000 years ago, human communication had become something far beyond what any other species had achieved. We weren't just making warning calls or signalings. Dominance. We were transferring complex information between minds. Think about what this means practically. Before sophisticated language, if you learned something valuable, it died with you. You might figure out that a particular root is edible if you cook it a certain way. That's valuable knowledge that took trial and error, maybe watching other people get sick, certainly risking your own life to discover. But when you die, that knowledge dies too, unless you can teach it to someone else. With language, knowledge becomes immortal. That root preparation technique can be passed to your children, who pass it to theirs, who pass it to theirs. One person's lifetime of learning can benefit thousands of people across hundreds of generations. Suddenly, you don't need to remember everything yourself. You just need to remember who to ask. This is cognitive outsourcing, and it's more radical than it sounds. Let's say you're living 30,000 years ago. Your group has maybe 50 people in it. Before language, each person needed to know everything necessary for survival. How to make fire, where to find water, which animals to hunt and how, which plants to eat, how to make tools, how to read weather patterns, how to treat injuries. That's an enormous amount of information to store in one brain. But with language, the cognitive load can be distributed. Maybe one person becomes really good at making tools. They practice constantly, learn all the best techniques, understand which stones produce the sharpest edges. Another person specializes in tracking animals. They memorize the habits of different prey species, learn to read tracks that others would miss. A third person becomes the plant expert, memorizing hundreds of different species and their properties. Now, instead of everyone needing to know everything, each person can specialize. And when you need knowledge outside your specialty, you just ask the expert. Your group's collective knowledge vastly exceeds what any individual could possibly retain. You've created an extended brain, distributed across 50 people, but functioning as a single cognitive system. This is the social brain hypothesis, and it explains something that has puzzled anthropologists for decades. Why did human brain size increase so dramatically during our evolution, but then stop growing? Because there's a limit to how much individual cognitive power you need once you have access to collective intelligence. The anthropologist Robin Dunbar noticed something fascinating about primate brain size. It doesn't correlate with environmental complexity or diet or tool use. It correlates with social group size. Primates with bigger brains live in bigger social groups. Not because managing social relationships is harder than other cognitive tasks, but because social relationships are the most valuable cognitive resource you can have. In a complex social group, your relationships are your survival insurance. The friend who shares food when you're hungry, the ally who helps you in conflicts, the mentor who teaches you valuable skills, the mate who helps you raise offspring. Managing these relationships requires sophisticated cognitive abilities. You need to track who owes favors to whom, who can be trusted, who is likely to help in different situations. You need theory of mind, the ability to understand what others are thinking and feeling. You need to predict behavior, negotiate agreements, maintain your reputation. But here's where it gets really interesting. Once you have these social cognitive abilities, you can use them to outsource other kinds of thinking. Dunbar calculated that humans can maintain stable social relationships with about 150 people. This number shows up repeatedly in human societies. It's the typical size of hunter-gatherer bands, the average number of people in Neolithic villages, the basic unit size of armies throughout history. 150 people is apparently the natural limit of our social brain capacity, but 150 people can collectively know vastly more than any individual could learn in a lifetime. If each person in your 150-person network has specialized knowledge, and you can access that knowledge through conversation, you essentially have a collective brain with 150 times the storage capacity of an individual brain. You don't need a bigger brain yourself. You need better networking. And humans got very, very good at networking. By 20,000 years ago, we weren't just maintaining local social groups of 150. We were creating extended networks that connected thousands of people across vast regions. Archaeological evidence from this period shows trade goods moving hundreds of miles from their sources, shell beads from coastal areas showing up in inland sites, obsidian from volcanic regions found in places far from any volcanoes, distinctive tool styles spreading across entire continents. This wasn't random drift. This was systematic knowledge sharing on a massive scale. A technological innovation developed in one group could spread to dozens of other groups within a few generations. A discovery about seasonal animal migrations could benefit people living hundreds of miles away. The collective human brain was getting bigger and more connected, even as individual brains stabilized in size. Then came writing. This was the next revolution in cognitive outsourcing, and it completely changed the rules of human knowledge. The earliest writing systems emerged around 5,000 years ago in Mesopotamia and Egypt, but simpler symbolic systems for recording information go back much further. Tally marks on bones dating to 20,000 years ago show our ancestors were already using external storage for numerical information. What writing did was make knowledge independent of memory entirely. Before writing, knowledge lived in human brains. It could be shared through teaching, but it had to be memorized. If you wanted to preserve important information across generations, you needed oral traditions, stories, and songs memorized exactly and passed down through careful teaching. This works, but it's limiting. Human memory can only retain so much. Complex technical information is hard to preserve accurately across multiple generations of oral transmission. Stories change slightly with each retelling. Details get lost or distorted. Writing changed everything. Suddenly you could record knowledge permanently in detail with perfect accuracy. An agricultural technique developed in one generation could be described precisely, recorded on clay tablets, and read by farmers centuries later. Astronomical observations could accumulate over lifetimes, building data sets too large for any individual to memorize. Legal codes could be standardized and preserved. Historical events could be documented. The collective human knowledge base began growing exponentially because nothing had to be forgotten anymore. And here's what's crucial for understanding brain evolution. Once you have writing, you need less individual memory. Why memorize star positions when you can write them down and consult the records? Why memorize every detail of crop rotation when you can keep agricultural manuals? Why store elaborate genealogies in your head when they're recorded in family documents? The cognitive load on individual brains decreased even as collective human knowledge expanded. Some anthropologists think this is precisely when human brain size began shrinking. The timing matches. Brain size started declining around 20,000 years ago, exactly when human societies were becoming complex enough that individual cognitive capacity mattered less than social connections and access to collective knowledge. By the time writing was invented 5,000 years ago, the trend was well established. Smaller individual brains were not a disadvantage if you had access to the extended cognitive system of human civilization. In fact, smaller brains might have been actively advantageous. Remember, brain tissue is expensive. It requires about 20% of your body's energy budget, while representing only 2% of your body weight. If you can get the same cognitive benefits from social connections and external information storage while spending less energy on your personal brain, that's a massive efficiency gain. The calories you save on brain maintenance can go toward other things: more muscle mass, better immune function, higher reproduction rates, This is exactly what we see in other species that have evolved collective intelligence. Ants are the classic example. Individual ants are not particularly smart. Their brains are tiny, containing maybe 250,000 neurons compared to about 86 billion in humans. A single ant can perform only simple behaviors: follow pheromone trails, pick up food, attack intruders, dig tunnels. But an ant colony is intelligent in ways that individual ants are not. Colonies make collective decisions about where to build nests. They allocate workers efficiently between different tasks. They adapt to changing environmental conditions. They wage sophisticated wars against competing colonies. They farm fungi and herd aphids. The colony as a whole exhibits problem-solving abilities that far exceed what any individual ant could accomplish. And here's the key point. As ants evolved more sophisticated collective behaviors, their individual brains didn't get bigger. They got more specialized. Different castes of ants have different cognitive abilities matched to their roles. Soldiers have enhanced aggression and threat detection. Foragers have better spatial navigation. Queens have enhanced longevity and reproductive systems but reduced mobility and defensive capabilities. The colony distributes cognitive labor the same way human societies do. No individual needs to be good at everything. The system as a whole just needs to cover all necessary functions. Humans aren't eusocial insects, but we're heading in a similar direction. As our societies grew more complex, we developed increasingly specialized roles. In a small hunter-gatherer band, everyone needs similar skill sets. But in an agricultural civilization with thousands of people, specialization becomes possible and advantageous. Some people become full-time toolmakers, developing expertise that would be impossible if they had to spend most of their time finding food. Others become farmers, learning intricate details of crop management that specialists can master but generalists can't. Others become traders, priests, administrators, soldiers. Each role requires its own cognitive specializations. A farmer needs to understand plant biology, weather patterns, and soil conditions, but doesn't need the spatial reasoning skills of a navigator or the social manipulation abilities of a politician. A craftsman needs fine motor control and understanding of material properties, but doesn't need to memorize genealogies or legal precedents. As specialization increased, natural selection could favor different cognitive profiles in different social niches. Someone born with exceptional spatial abilities might become a hunter or navigator. Someone with strong verbal skills might become a storyteller or negotiator. Someone with good hand-eye coordination and patience might become a toolmaker. The population as a whole maintains cognitive diversity, but individuals don't need to be cognitive generalists anymore. You need to be really good at your specialty and capable of basic social interaction. Everything else can be outsourced to other people. This is radically different from how human evolution worked for millions of years. Throughout most of our evolutionary history, generalists survived and specialists died. If you could only do one thing well, you were vulnerable. Circumstances might change and your specialty might become irrelevant. But in a large, stable society, specialists can thrive because the society buffers them from environmental changes. If drought kills the crops, farmers might struggle, but the society as a whole can support them through stored resources and trade until conditions improve. And then we invented technology. Not just simple tools, but genuine cognitive prosthetics. External devices that extend and enhance our mental capabilities. The abacus was one of the first. Humans are not naturally good at arithmetic with large numbers. Our brains evolved to estimate quantities approximately. which was fine for most of evolutionary history. But complex civilizations need precise calculations for trade, taxation, construction, astronomy. The abacus outsources this calculation to a physical device. You don't need to be a mathematical genius to use an abacus. You just need to know the rules for moving beads. The device itself handles the cognitive load of keeping track of digits and carrying operations. Books did something similar for memory. Instead of training yourself to memorize vast amounts of information, you could write it down and look it up when needed. Medieval scholars who would have spent years memorizing texts could instead spend that time analyzing and synthesizing information from multiple sources. Telescopes and microscopes extended our sensory capabilities beyond biological limits. You don't need better eyes if you have instruments that can show you things no biological eye could ever see. Compasses and sextants outsource navigation, letting people traverse oceans without needing the spatial memory of migrating birds. Clocks gave us precision timekeeping far beyond our biological circadian rhythms. Each technology reduced the cognitive load on individual humans, while expanding what humans collectively could accomplish. And we're still accelerating this process. Calculators mean you don't need mental arithmetic skills. GPS means you don't need to memorize routes or read maps. Smartphones mean you don't need to remember phone numbers, addresses, schedules, or facts. You can look up anything instantly. Your phone is literally an external memory system, storing information that previous generations would have had to memorize. Some people worry this is making us stupid. If we outsource too much cognition to technology, will our brains atrophy? Are we domesticating ourselves, becoming dependent on our technological crutches the way domestic animals depend on human care? Maybe. But maybe that's not actually a problem. If the measure of intelligence is not what an individual brain can do, but what a human being with access to their full technological and social network can accomplish, then we're smarter than we've ever been. A modern high school student with a smartphone and internet access has more information available than the greatest scholars of ancient Alexandria. They might not have memorized as much, but they can learn about virtually any topic in minutes. They can solve problems that would have baffled the greatest minds of previous generations, not because their individual brains are superior, but because they're plugged into a vast cognitive network. This is the extended brain hypothesis taken to its logical conclusion. Your brain is not the 3 pounds of neurons in your skull. It's that, plus your social network, plus your books and devices, plus the entire accumulated knowledge of human civilization that you can access through technology. And that extended brain is still growing, still getting smarter, even as the biological component potentially shrinks. Which brings us to a fascinating and slightly unsettling question. If we're evolving to have smaller individual brains while our collective intelligence expands, where does this process end? Could we eventually become like ants, with highly specialized individuals who are cognitively limited on their own, but collectively intelligent as a civilization? Could we become truly dependent on technology, unable to survive without our cognitive prosthetics? Some futurists think we're headed toward a kind of technological singularity, where human and machine intelligence merge completely. Your brain won't be the thing doing the thinking anymore. It'll just be the interface between your consciousness and vast computational systems. Others think we'll enhance biological brains with technology, implanting computers directly into neural tissue. Your brain might get smaller, but it'll be augmented with processors and memory storage that far exceed biological limits. Still others think we'll maintain a balance. Some biological cognitive capacity retained for things brains do well: emotional processing, creativity, social intuition, while outsourcing other functions to technology and social systems. Nobody knows which path we'll take. But what's clear is that the old model of human intelligence, the isolated individual brain solving problems through raw cognitive power, that model is obsolete. We evolved past it 20,000 years ago when we learned to distribute cognition across social networks, and we've been accelerating away from it ever since. Your brain doesn't need to be bigger because you're never really alone in your thinking. Every time you Google something, ask a friend for advice, use a calculator, or reference a book, you're tapping into the extended brain of human civilization. That brain is millions of times larger than any individual brain could be. It contains the accumulated knowledge of every human who ever lived and recorded their insights, and it's still growing, still evolving, still getting smarter. So maybe our brains stopped growing 20,000 years ago because they didn't need to grow anymore. We'd found a better solution. Instead of making individual brains bigger, we made civilization itself into one vast distributed cognitive system, and we became its cells, specialized, components of something far larger and smarter than any of us could be alone. But here's where we need to talk about the theory that keeps evolutionary biologists up at night, the one that makes people uncomfortable at dinner parties. The possibility that our brains didn't stop growing 20,000 years ago because we reached some optimal configuration. The possibility that they stopped growing because we started devolving. Now, before you click away thinking this is some pseudo-scientific nonsense, understand this is a genuine scientific debate. There are legitimate researchers with impressive credentials who look at the evidence and see signs of evolutionary regression. They're not cranks. They're not pessimists. They're scientists following the data to its most uncomfortable conclusion. The argument goes like this. For millions of years, natural selection was brutal and efficient. Individuals with better brains, sharper thinking, stronger problem-solving abilities had survival advantages. They were more likely to find food, avoid predators, navigate social hierarchies, attract mates, and successfully raise offspring. Every generation, the genes that built better brains got passed on more frequently. The genes that built inferior brains died out. This process, repeated over millions of years, drove the incredible expansion of human brain size, from Australopithecines with 450C brains to Homo erectus with 900C and C, to archaic humans with 500C to peak humans 20,000 years ago with 500cc brains. Each increase represented countless generations of selection pressure favoring intelligence, memory, planning ability, social cognition. But then something unprecedented happened. We invented civilization, and civilization changed everything. Think about what life was like for your ancestors 50,000 years ago. Every day was a cognitive challenge. Where are the game animals? Which plants are safe to eat? How do we track weather patterns? Where should we make camp? Who can we trust? Who's cheating the group? Every decision mattered. Make the wrong choice about food sources and you starve. Misjudge social dynamics and you get expelled from the group. Fail to plan for winter and you freeze to death. Under those conditions, intelligence was survival. The smartest individuals in each generation were significantly more likely to live long enough to reproduce. Natural selection was doing its job, constantly winnowing out cognitive deficiencies and promoting cognitive advantages. But then we domesticated plants and animals. We built permanent settlements. We developed agriculture, trade, specialization of labor. And suddenly, survival stopped requiring peak cognitive performance. You didn't need to be a genius to survive as a farmer. You needed to follow established procedures, plant in spring, harvest in fall, store grain for winter, repeat. The knowledge was cultural, passed down through generations. Individual innovation was less important than tradition and conformity. As civilizations grew more complex, this effect intensified. Cities created buffers against natural selection. Food storage meant temporary poor planning didn't result in starvation. Social safety nets meant individuals who would have died in hunter-gatherer societies could survive and reproduce. Medicine meant genetic conditions that would have been fatal became manageable. Don't misunderstand this argument. This isn't saying civilization was bad or that we should have stayed hunter-gatherers. This is about evolutionary pressures, about what happens when you remove the selective forces that have been shaping a species for millions of years. The dark theory suggests that over the past 20,000 years, as our brains have been shrinking, we've been accumulating deleterious mutations. Genetic errors that would have been quickly eliminated by natural selection in the past, but now persist because civilization cushions their effects. Research by geneticist Gerald Crabtree at Stanford published this controversial hypothesis in 2012. He calculated that human intellectual capabilities are determined by perhaps 2,000 to 5,000 genes. Each of these genes is vulnerable to mutation. Crabtree estimated that in the 120 generations since the dawn of agriculture, each of us has probably accumulated 2 or more mutations in these genes that would have been disadvantageous in hunter-gatherer environments. His conclusion was stark. A hunter-gatherer who did not think correctly could more easily die, leading to selection against mutations that decreased brain function. In contrast, a modern society member with decreased intellectual and emotional abilities can still thrive because of social structures and medical interventions. In other words, we're not just failing to get smarter anymore, we might actively be getting dumber generation by generation. Now, before this gets too depressing, let's look at the counter-argument, because there is one, and it's powerful, the Flynn effect. Named after researcher James Flynn who documented it, this effect shows that IQ scores have been rising consistently across the developed world for the past century. About 3 IQ points per decade. This is a massive increase. Someone scoring average in 1,920 would score in the borderline intellectual disability range by today's standards. How do we reconcile this with shrinking brains and accumulating mutations? How can we be getting simultaneously dumber and smarter? The answer might be that we're measuring different things. IQ tests measure problem-solving ability, pattern recognition, abstract reasoning, skills that are heavily influenced by education, nutrition, exposure to complex environments. The Flynn effect might simply be showing that modern environments, modern education, better nutrition, reduced childhood disease are allowing people to develop closer to their genetic potential, but genetic potential itself might be declining. Think of it like this. You have a car engine with incredible theoretical performance. That's your genetic potential. But if you put low-quality fuel in it, never change the oil, and don't maintain it properly, it won't perform well. That's like growing up in poverty with poor nutrition and no education. The Flynn effect shows we've gotten much better at maintaining the engine. Better fuel, better maintenance, better conditions. So performance has improved dramatically, but the engine itself, the underlying genetic blueprint, might actually be degrading slowly. We just haven't noticed because we've gotten so much better at maintenance. This creates a troubling scenario. What happens if civilization experiences a disruption? If our social structures, educational systems, and medical technologies fail, even temporarily? Would we discover that our actual genetic cognitive capacity has declined substantially from our ancestors? Some researchers think we already have evidence this is happening. Studies of reaction time, a simple measure less influenced by education than IQ, have shown concerning trends. Victorian-era data suggests people in the 1800s had faster reaction times than modern populations. Reaction time correlates with neural processing speed. It's measuring something fundamental about how quickly your brain works. If reaction times are slowing while IQ scores rise, that suggests the Flynn effect is masking an underlying biological decline. We're getting better at leveraging whatever cognitive capacity we have, but that capacity itself might be diminishing. Then there's the medical technology factor. This is where the argument gets really uncomfortable, because it involves real people and real medical conditions. But from a purely evolutionary perspective, modern medicine has undoubtedly altered natural selection pressures. Conditions that would have been fatal in the past are now manageable or curable. Genetic disorders that would have prevented reproduction can now be treated, allowing affected individuals to have children and pass on those genes. This isn't a value judgment. These are incredible humanitarian achievements. Nobody's suggesting we should stop treating diseases or helping people live full lives. But it does have evolutionary consequences. Every genetic condition we can now manage adds to the mutational load of the population. Over many generations, this accumulation could become significant. Type 1 diabetes was fatal before insulin was discovered. Now it's manageable, and people with genetic predisposition to diabetes can live normal lives and have children. Severe myopia would have been a major disadvantage for hunter-gatherers. Now we have glasses and contact lenses and LASIK surgery. Countless genetic conditions from haemophilia to certain heart defects to immune disorders that once prevented reproduction are now treatable. Again, this is wonderful from a humanitarian perspective, but it means natural selection is no longer removing these mutations from the gene pool. They're accumulating generation by generation. Some evolutionary biologists worry we're essentially building up an evolutionary debt, a burden of deleterious mutations that's only manageable as long as our technological civilization continues. If civilization were to collapse, if we lost access to modern medicine and agriculture and all the buffers that protect us from natural selection, the accumulated genetic load might become catastrophic. This scenario was popularized somewhat crudely by the movie Idiocracy. The idea that less intelligent people reproduce more, while more educated people have fewer children, leading to a gradual decline in population intelligence over generations. There's some truth to the demographic patterns. Education level does inversely correlate with fertility rates in modern societies. People with advanced degrees have fewer children on average than those without. If intelligence is heritable, and it is, about 50–80% according to twin studies, then differential fertility rates based on education could theoretically shift population-level intelligence over time. But here's where the Idiocracy scenario falls apart. It dramatically oversimplifies both genetics and social dynamics. Intelligence isn't controlled by a handful of genes that can be simply bred in or out of a population. It's polygenic, influenced by thousands of genes with complex interactions. It's also heavily influenced by environment. Two parents with genius-level IQs can have average children. Two average parents can have highly intelligent children. Regression to the mean is powerful. Moreover, the relationship between education and intelligence is complicated. Not everyone with advanced degrees is highly intelligent, and not everyone without formal education is unintelligent. Using education as a proxy for genetic intelligence is deeply problematic. More fundamentally, natural selection doesn't care about our definitions of intelligence. It only cares about reproductive success. In modern environments, the traits that lead to reproductive success might be completely different from those that led to success in ancestral environments. Social skills, emotional intelligence, and conscientiousness might matter more than raw cognitive ability. So the idiocracy scenario is almost certainly wrong, or at least vastly oversimplified. But that doesn't mean the underlying concern is baseless. The question remains whether removing natural selection pressures through civilization has evolutionary consequences we should be thinking about. Some species provide cautionary examples. Cave-dwelling fish that lost their eyes over thousands of generations because sight provided no advantage in total darkness, and maintaining eyes is metabolically expensive. Flightless birds on islands without predators whose wings atrophied because flight was no longer necessary for survival. When natural selection stops favoring a trait, that trait can degrade through what's called relaxed selection. Mutations that harm the trait are no longer selected against, so they accumulate. Eventually, the trait can disappear entirely or become vestigial. Could this happen to human intelligence? Are we like those cave fish, living in an environment where peak cognitive ability is no longer as strongly selected for? The counter-argument is that human intelligence is different from fish eyes or bird wings. Our intelligence is what creates and maintains civilization. It's not like we've moved into an environment where thinking is unnecessary. We've moved into an environment we created through thinking, and maintaining that environment requires continued intelligence. Moreover, sexual selection might still be operating. Humans choose mates based partly on perceived intelligence. Humor, conversation ability, and problem-solving skills are attractive. This cultural selection might partially compensate for reduced natural selection. There's also gene-culture coevolution to consider. As our culture has become more complex, it's created new selection pressures. The ability to learn from others, to navigate social hierarchies, to cooperate in large groups, these might be under stronger selection now than in ancestral environments. Some researchers argue brain size reduction might actually reflect selection for these social and cultural abilities rather than raw cognitive power. Smaller brains are metabolically cheaper. If you can achieve the same or better problem-solving through social learning and cultural transmission, why maintain an expensive large brain? This would make the brain reduction an efficiency upgrade rather than devolution. We're not getting dumber, we're getting better at leveraging cultural knowledge and social cooperation, which allows us to achieve more with less individual brain tissue. But the dark theory persists because we simply don't know. We're conducting a massive, unplanned evolutionary experiment on ourselves. We've removed or dramatically weakened most natural selection pressures that shaped us over millions of years. We're living in environments radically different from those we evolved for. We're accumulating mutations that would have been eliminated in the past. The optimists say this is fine, evolution is ongoing. We're adapting to new environments through new mechanisms. Cultural evolution has taken over from biological evolution, and it's far faster and more efficient. The pessimists say we're building a house of cards. Our technological civilization is masking an underlying biological decline that will become apparent if or when that civilization falters. The truth is probably somewhere in between. Yes, we're accumulating mutations that would have been selected against in the past. Yes, our brains have shrunk from their peak size. Yes, we're living in ways that dramatically reduce natural selection on cognitive traits, but we're also developing new capabilities. Better at abstract reasoning, better at learning from others, better at cooperating in large groups. These might be genuine evolutionary advances, just different from the raw brain size increases of the past. The real concern isn't whether we're devolving, It's whether we're evolving fast enough to keep up with the pace of environmental change we're creating. Climate change, environmental degradation, social upheaval, technological disruption. We're transforming our world faster than evolution can respond. That's the actual dark theory. Not that we're getting dumber, but that we've decoupled our evolution from our environment so severely that we're increasingly maladapted to the world we're creating. Our brains evolved for small group living, face-to-face interaction, immediate physical threats and concrete problems. Now we live in cities of millions, interact through screens, face abstract existential threats, and grapple with problems of such complexity that no individual can fully understand them. The fact that our brains stopped growing 20,000 years ago means we're facing 21st century challenges with Stone Age hardware. And maybe that's the real question we should be asking. Not whether we're devolving, but whether the evolution that shaped us has left us equipped for the future we're creating. Because one way or another, evolution isn't done with us. The question is whether we're directing it or just along for the ride. So our brains stopped growing 20,000 years ago. They've been shrinking ever since. We've explored theories about efficiency upgrades, diet changes, and social outsourcing. But here's the thing that keeps neuroscientists and evolutionary biologists awake at night. Evolution didn't stop. It never stops. It just changes direction. And right now, at this exact moment, our brains are evolving in ways that would seem like science fiction to someone from even 100 years ago. The question isn't whether human brains will continue evolving. The question is, what are they evolving into? Let's start with what's happening right now. Not over millions of years, not over thousands, right now, today. As you watch this video, your brain is being shaped by forces that didn't exist even 50 years ago. This is evolution in real time, and it's happening faster than anything our ancestors experienced. Consider this. The average human born today will have fundamentally different neural architecture than someone born in 1950. Not because of genetic changes, those take longer, but because of neuroplasticity, the brain's ability to rewire itself based on experience. And what experiences are modern brains having? Constant digital stimulation, information overload, social media, smartphones, video games, streaming content, GPS navigation, search engines. Every single one of these technologies is rewiring human brains right now in measurable ways. Neuroscientists using MRI technology have documented specific structural changes in people who use smartphones heavily. The cortical regions responsible for thumb movement have expanded, literally. Your brain is devoting more neural real estate to controlling your thumbs because you use them constantly for texting and scrolling. That's not a metaphor. That's observable physical change in brain structure happening within a single lifetime, but that's just the beginning. GPS navigation is causing measurable atrophy in the hippocampus, the region responsible for spatial memory and navigation. London taxi drivers, who spend years memorizing the city's streets without GPS, show significantly larger hippocampi than average people. But studies of people who rely heavily on GPS show the opposite effect. Their spatial processing regions are literally shrinking from disuse. This is evolution through technology. Not genetic yet, but it sets the stage for genetic changes if these patterns continue for enough generations. If humans who can't navigate without GPS survive and reproduce just as successfully as those who can, and if everyone starts using GPS, the genetic variations that support complex spatial memory might become less common, not because they're selected against, but because they're no longer selected for. They become evolutionarily neutral, and neutral traits tend to drift randomly over time. The same thing is happening with memory itself. Why memorize information when you can Google it instantly? Why develop deep reading skills when you can skim summaries? Why practice mental math when you have calculators? Each of these conveniences is removing selection pressure for certain cognitive abilities. And here's where it gets really interesting, or really concerning depending on your perspective. These changes are happening so fast that genetic evolution can't keep up. Neuroplasticity is carrying the load. But neuroplasticity has limits. It can rewire existing neural architecture, but it can't create fundamentally new capabilities. That requires genetic changes, mutations that alter brain development from the ground up. And those changes take time. Lots of time. Unless we speed them up. Enter genetic engineering. Specifically, CRISPR and other gene editing technologies that allow us to make precise changes to DNA. We're not talking science fiction anymore. We're talking about technologies that exist right now, that are being used in laboratories worldwide. In 2018, a Chinese scientist named He Jiankui announced he had used CRISPR to edit the genomes of human embryos, creating the first gene-edited babies. The international scientific community was horrified, not because the technology didn't work, but because it did. We now have the ability to edit human genes, including genes that affect brain development, and we're just getting started. Researchers have identified hundreds of genetic variants associated with intelligence, memory, processing speed, and other cognitive traits. Most of these variants have tiny individual effects, but collectively they influence cognitive ability significantly. In principle, not yet in practice, but in principle, we could use CRISPR to select for these variants in embryos. We could create humans with enhanced cognitive abilities, not through millions of years of natural selection, but through deliberate genetic engineering. This raises profound questions. Should we? Who decides? Who gets access? What happens when some humans are cognitively enhanced and others aren't? But setting aside the ethical minefield for a moment, let's focus on the practical question. What would genetically enhanced human brains actually be like? The obvious approach would be to increase brain size again, reverse the shrinkage that's been happening for 20,000 years. But here's the problem. There are hard physical limits. Human babies already have massive heads that barely fit through the birth canal. Making them bigger would require either redesigning the female pelvis, which has its own complications, or switching entirely to caesarean births. Both options are technically possible, but socially and medically complex. The alternative is to make brains more efficient without making them bigger, increase neuron density, improve synaptic transmission, enhance blood flow to support higher metabolic activity, optimize neurotransmitter production. These are all theoretically achievable through genetic engineering, and they wouldn't require larger skulls. But there's an even more radical possibility: brain-computer interfaces. Why limit ourselves to biological neurons when we can integrate electronic components directly into neural tissue? This isn't science fiction either. Elon Musk's company Neuralink is currently developing implantable brain-computer interfaces. Other companies and research institutions are pursuing similar technologies. The current generation of devices is primitive, designed mainly to help paralyzed people control computers or prosthetic limbs. But the trajectory is clear. These technologies will become more sophisticated, more integrated, more capable. Eventually, and probably within our lifetimes, we'll have the ability to augment human cognition directly with electronic components. Memory expansion modules, processing accelerators, direct neural connections to the internet. This would represent something unprecedented in evolutionary history, the merger of biological and artificial intelligence into a hybrid system that's neither purely organic nor purely electronic. Think about what that means. For 4 billion years, evolution has worked through biological mechanisms: DNA mutations, natural selection, genetic drift. Even the most sophisticated organisms were built entirely from biological materials: cells, proteins, neurons. But now we're on the threshold of mixing biological and electronic components at the fundamental level. Not just using tools, our ancestors did that. Not just relying on external technology, we've been doing that for millennia. Actually integrating non-biological components into our bodies and brains. This would be a transition as profound as the evolution of multicellular life or the development of consciousness itself, and it's probably going to happen within the next 50 to 100 years. But let's not get too focused on intentional enhancement. Evolution doesn't care about our plans. It responds to whatever selection pressures actually exist, and right now we're creating new selection pressures that have nothing to do with our enhancement fantasies and everything to do with the environmental catastrophe we're living through. Air pollution is affecting brain development worldwide. Studies show children raised in high pollution areas have measurably smaller brains and reduced cognitive function compared to those in clean environments. This is happening right now, affecting hundreds of millions of children globally. If this continues for generations, it will create selection pressure. Individuals with genetic variants that protect brain development from pollution damage will have cognitive advantages. Those variants will increase in frequency. Will evolve pollution resistance, but at the cost of average brain development in unpolluted environments. The same thing is happening with diet. The modern Western diet, high in processed foods and low in nutrients, is terrible for brain development. But it's incredibly prevalent. Children raised on this diet show different patterns of brain development than those on healthier diets. If this continues long enough, we'll see genetic adaptation. Variants that help brains develop normally despite poor nutrition will become more common. We'll become adapted to junk food, which sounds convenient until you realize what it means. Our brains will be optimized for surviving in a degraded nutritional environment, not for reaching their maximum potential. Then there's the lifestyle factor. Modern humans are incredibly sedentary compared to our ancestors. We sit for hours daily, starting in childhood. This affects everything from bone density to cardiovascular health to, yes, brain development. Physical exercise promotes neuroplasticity, enhances memory formation, and supports cognitive function. When we don't exercise, we don't get these benefits. Over time, if sedentary lifestyles persist, we might see genetic adaptation that reduces the benefits of exercise. Why maintain expensive neural mechanisms that depend on physical activity if nobody's physically active anyway? This is devolution in action, adaptation to a degraded environment resulting in reduced capabilities. But perhaps the most fascinating possibility is evolutionary divergence. For the first time in hundreds of thousands of years, human populations might begin diverging into distinct species again. Not through geographic isolation this time, through technological and social isolation. Consider wealthy populations with access to genetic enhancement, brain-computer interfaces, and optimal developmental environments might begin diverging genetically from populations without these advantages. Not quickly. Evolution takes time. But over thousands of years, the cumulative effect could be significant. We could end up with human subspecies or even separate species. enhanced humans with genetically optimized brains and technological augmentation, baseline humans without access to enhancement technologies, and possibly adapted humans, populations that have evolved specific adaptations to degraded environments. There's also the space factor. If humans establish permanent colonies on Mars or other worlds, those populations will face radically different selection pressures. Lower gravity affects skeletal development and muscle mass. Radiation exposure might select for enhanced DNA repair mechanisms. Confined environments might favor different social behaviors and cognitive styles. Within a few thousand years, space colonists could diverge noticeably from Earth populations. Within tens of thousands of years, they could become separate species, unable to interbreed even if they wanted to. We'd have Martian humans, asteroid belt humans, moon humans, all descendants of Earth populations but evolutionarily distinct. So what do all these trends suggest about the actual trajectory of human brain evolution? Let's try to project forward, understanding that these are informed speculations, not predictions. In 1,000 years, genetic changes will be minimal. That's only about 40 generations, not enough for significant evolution through natural selection alone. But it's plenty of time for genetic engineering to become widespread if we choose that path. By the year 3000, we might see two distinct human populations: naturals who avoided genetic modification and enhanced humans who embraced it. The enhanced would probably have brains optimized for efficiency rather than size. Better synaptic transmission, enhanced metabolic support, improved resistance to neurodegenerative diseases. They might also have brain-computer interfaces as standard, installed in childhood or even prenatally. In 10,000 years, about 400 generations, we're looking at enough time for significant natural evolution, especially if selection pressures are strong. If environmental degradation continues, we might see humanity adapt to polluted, nutrient-poor environments. Brains might become smaller still, but more efficient per unit mass. If enhancement technologies become universal, natural selection might actually weaken. Why evolve better brains naturally when everyone gets electronic upgrades anyway? This could lead to what biologists call domestication syndrome, reduced cognitive abilities in the biological substrate because technology compensates for all deficits. We'd become dependent on our enhancements, unable to function without them, like modern humans unable to navigate without GPS, but much more extreme. In 100,000 years, well, all bets are off. That's 5 times longer than the period since our brain started shrinking. It's enough time for dramatic evolutionary changes, possibly even speciation events. If humanity has spread to other star systems by then, we'd almost certainly see multiple human species, each adapted to different worlds. Earth humans might have integrated so completely with technology that the distinction between biological and artificial becomes meaningless. Their brains might be hybrid organic electronic systems, barely recognizable as related to our current brains. Mars humans might have larger brains to compensate for lower gravity's effects on body size, or smaller brains if the metabolic costs prove too high. Space station humans living in zero gravity might develop entirely different body plans and neural architectures. But here's the really profound question that all of this raises. Should we accept these evolutionary processes, or should we take control? Natural evolution is blind. It doesn't care about human flourishing or consciousness or art or science. It only cares about reproduction, about genes getting copied. If our brains shrinking makes us reproduce more successfully, evolution considers that a success, even if it makes us less intelligent. If adapting to pollution means reduced cognitive capacity, evolution accepts that trade-off without hesitation. But we're not blind. We can see these trajectories, we can understand the costs and benefits. So shouldn't we intervene? Shouldn't we use genetic engineering, not to create superhuman intellects, but just to maintain the cognitive capabilities we already have? To prevent adaptation to degraded environments? To ensure humanity doesn't devolve into pollution-resistant, junk food-adapted, technology-dependent organisms barely capable of independent thought? The counter-argument is equally compelling. Evolution has been optimizing life for 4 billion years. It's produced consciousness, intelligence, creativity, all without any intentional design. Who are we to think we can do better? Every time humans try to engineer biological systems, we create unintended consequences. Antibiotic resistance, ecological disasters from introduced species, genetic diseases from inbreeding. What makes us think we can successfully engineer human brains without creating catastrophic problems? Maybe we should trust evolution, clean up our environment, maintain healthy lifestyles, and let natural selection continue doing what it's always done, optimizing organisms for their actual environments, not for some idealized environment that doesn't exist. There's no easy answer. Both positions have merit. But here's what we know for certain. The evolution of the human brain didn't stop 20,000 years ago when our skulls reached their maximum size. It didn't stop when our brains started shrinking. It's continuing right now, shaped by smartphones and pollution, and processed foods and sedentary lifestyles and genetic engineering and brain-computer interfaces. All of these factors are influencing which genes get passed to the next generation and how those genes are expressed during brain development. We're living through an evolutionary transition right now, one that's happening faster than any transition in human history, because technology is accelerating everything. The human brain in 1,000 years, let alone 100,000 years, will be as different from our current brains as our brains are from those of Homo erectus. Maybe different in good ways, enhanced and optimized and augmented, maybe different in bad ways, diminished and dependent and adapted to degraded conditions. Probably different in ways we can't even imagine, shaped by technologies and social structures and selection pressures that don't exist yet. But different, certainly. Evolution never stops. It just changes direction. And right now, we're at one of the biggest turning points in the 300 million year history of the vertebrate brain. The mystery isn't why our brains stopped growing 20,000 years ago. The mystery is what they're becoming right now in this moment, as evolution continues its endless work of optimization, adaptation, and transformation. We're not the endpoint of human evolution. We're not even close. We're somewhere in the middle of a story that started with those 1,280 survivors of the genetic bottleneck and will continue for millions of years into a future we can barely imagine. The evolution we never finished isn't something that happened in the past. It's happening right now. It's happening to us. And in a very real sense, we're just starting to realize we have a choice about where it goes next. So here we are, at the end of a journey through 20,000 years of brain evolution that seemingly stopped. We've examined the golden age when our ancestors carried brains that were, on average, 10% larger than ours today. We've tracked the great shrinkage that began around 20,000 years ago and continues even now. We've explored 4 major theories: the efficiency upgrade, the diet revolution, social outsourcing, and the uncomfortable possibility that we're devolving. But here's the truth. We still don't definitively know why our brain stopped growing. And you know what? That's actually the most honest answer anyone can give you. Because evolution doesn't happen on timescales that human beings are designed to comprehend. We live 80, maybe 90 years if we're lucky. We think in terms of decades. Evolution thinks in terms of millennia, hundreds of thousands of years, millions of years. To evolution, 20,000 years is basically yesterday, a blink, a moment so brief it barely registers. The evidence we have suggests that all four theories probably contain pieces of the truth. Our brains likely did become more efficient, with white matter increasing relative to grey matter, neural connections becoming more streamlined, cognitive processes requiring less raw computational power to achieve the same results. This isn't speculation. We can see it in brain imaging studies comparing modern humans to reconstructions of ancient brain structures. The diet and lifestyle revolution definitely played a role too. When you stop spending 80% of your waking hours hunting, gathering and processing raw food, when you develop cooking techniques that pre-digest nutrients, when you create agriculture that provides reliable calories, your brain can afford to shrink. You don't need the massive energetic engine anymore because your environment has become less cognitively demanding in certain specific ways. Social outsourcing is probably the most important factor of all. Once you develop complex language, writing systems, mathematical notation, and eventually computers and the internet, you don't need to store everything in your individual skull. You can distribute cognitive tasks across your entire society. You can build libraries and databases and search engines. You can specialize, becoming an expert in one narrow domain while relying on others to handle everything else. In a very real sense, human civilization has become a kind of extended brain, a collective intelligence far more powerful than any individual could achieve alone. But here's where it gets really interesting. What if the shrinkage isn't actually a problem? What if we're looking at this all wrong? We've been assuming that bigger is better, that our Ice Age ancestors with their massive skulls were somehow superior to us. But maybe that's backwards. Maybe their brains were big because they had to be, because their environment was so harsh and unpredictable that they needed every bit of raw processing power just to survive. They didn't have the luxury of efficiency. They needed brute force cognition. We, on the other hand, have built a world that allows our brains to be smaller and more efficient. We've created stable environments, reliable food supplies, educational systems that can teach complex skills quickly. We've developed technologies that amplify our cognitive abilities far beyond what raw brain tissue alone could achieve. A modern teenager with a smartphone and internet connection has access to more information than any Ice Age genius could have accumulated in a lifetime. So maybe the question isn't, why did our brains stop growing? Maybe the question is, why would they need to keep growing? We've essentially hacked evolution. We've created an artificial environment that reduces selection pressure for raw brain size while simultaneously increasing our collective intelligence to unprecedented levels. But, and this is crucial, we're not done evolving. Evolution never stops. It just changes direction based on new selection pressures. Right now, in the modern world, we're creating entirely new evolutionary pressures that our ancestors never faced. Sedentary lifestyles, processed foods, digital environments, social media. Each of these represents a novel challenge that our brains and bodies must adapt to. The question is, what will we become? Some researchers think we're entering a period of rapid cognitive evolution driven by technology. Not biological evolution in the traditional sense, but something new, cyborg evolution. the merging of human cognition with artificial intelligence, brain-computer interfaces, genetic engineering. We might be on the verge of taking control of our own evolution in ways that would have been unimaginable to our Ice Age ancestors. Others worry that we've created environments so divorced from our evolutionary heritage that we're experiencing widespread cognitive and psychological problems, anxiety, depression, attention disorders. Maybe these aren't just medical conditions. Maybe they're symptoms of a species living in a world it didn't evolve for. Maybe the brain shrinkage is the first sign that we've built a civilization that's fundamentally incompatible with human neurology. The truth is probably somewhere in the middle. We're adapting constantly in ways both positive and concerning. Our brains are still changing, still evolving, just not necessarily getting bigger. The evolution we never finished might actually be the evolution we're living through right now, in real time, too close to see clearly. This mystery matters because it's ultimately about understanding who we are and where we're going. If we can figure out why our brains shrank, we might better understand how to use them effectively in the modern world. We might identify problems before they become crises. We might even guide our own evolution in positive directions. So I want to hear from you. Which theory do you think best explains the brain shrinkage? The efficiency upgrade, diet and lifestyle, social outsourcing, or are you worried we're actually devolving? Drop a comment below and let me know where you're watching from, and if you found this journey through human evolution fascinating. Hit that like button and subscribe because we're going to keep exploring the mysteries of human history and the strange ways evolution has shaped us into what we are today. Because here's the final thought I want to leave you with. Maybe our brains didn't stop evolving 20,000 years ago. Maybe they just transformed in ways we don't yet recognize. Maybe the story of human evolution isn't written in skull size or brain volume. Maybe it's written in the cities we build, the technologies we create, the knowledge we accumulate across generations. Maybe we're not smaller. Maybe we're just different. And maybe that's exactly what we need to be. The mystery remains, but we're not done yet. Not even close.